So next speaker is Conny Ohult, and he's a technical leader for Cisco NSO as well, and he will talk about designing for maximal transaction throughput on Cisco NSO.
All right, so it's a bit deceiving, the title here, how to limit the concurrence of NSO. And designing for maximal throughput, it's kind of a, we realized we were two technical leaders, realized we were doing the same presentation, so we just merged them. So we'll be talking about both achieving transaction throughput with using concurrency, and also show you how to, if you don't want the concurrency, what do you do then? And try to go through that at the same time, step through it, and then there will be a lab after the break where you can get some hands-on to actually try out the different variants that I'll quickly go through here in this half hour, right? So as Fabrizio mentioned, my name is Conny Andersen, and yeah, I worked for a couple of years now with documentation and examples, basically trying to help users of NSO integrate with NSO in the best way possible to be able to utilize all the functionality in this wonderful product that we love so much. And before that, been working a lot with doing the same thing, but as a solution architect, helping users integrate with both Conf and with NSO for 8-9 years before that. So I was here just before this became a Cisco product, and went through that. Okay, so when we talk about concurrent transactions and maximizing throughput, we often talk about CPUs and CPU cores. It's easy to get limited by one core, and then you need a lot of CPUs and you need some elaborate setups and so forth to achieve the kind of throughput that you could maybe do with just one CPU, or I mean one processor, multi-core processor with several CPU cores. This one has 10. There's many of them today that have 100 or something like that. And how do you do that with NSO? And how do you prevent it too if you want to? If you don't want to be environmental, or if you don't like concurrency because it's not the way we humans think. We think basically most of the time in a sequential order. So I mentioned that there's a lab. There's also documentation, which is quite new. I mean, it's been around for a while. We try to expand the documentation for NSO with regards to transactions and throughput and scalability and so forth, especially after NSO 6, where that opened up a whole array of possibilities that you'll see here. Yes, so here's the link. I'll repeat the link later, and for you, those of you who come to the lab after the break, I'll direct you there too, and you can try it. It's also in the agenda, I think, the link to it. So what you see right here is the NSO. Let's see if I can do this. Yeah. So what you see here is basically a high-level view of an NSO transaction. An NSO transaction is triggered then, as you might know, by, you have a RESTconf patch, for example, or you have a netconf edit config, or you do some CLI stuff and you commit it. When you commit, the transaction starts. You do a MAPI thing through the management agent API, and you do an apply, and that starts the transaction. Or actually, non-service redeploy starts a transaction as well. And we'll get to what I mean by the non-service part. Maybe we can cover it in this session. Otherwise, we'll go through it in more detail in the next session. Okay, so it starts with NSO, then gets the CLI commit, for example, starts the transaction. There's minimum diff being calculated by NSO, checking, okay, what's in CDB, the database, and what is this transaction supposed to do? And what's the actual changes that are going to happen here? Then there's some pre-validation, and the service create callback is called if you have a service that is going to then map to a device, Yang model device schema, and then be pushed to device. That service create is called here in this transhooks phase. Then in this read write here, there's a service write log, which you might have seen if you checked out the logs like developer log or progress trace log. This is basically for checking that there's no conflicts between between transactions executing in concurrently. So we'll get back to that again. After this transhook, the service create, you have a validation phase, young validation. You might have some call points in Python, Java, for example, Erlang, where you want to check some things and validate. And after this validation phase, the transaction lock is taken. We check, okay, is there any conflicts? Well, yes, there was conflict, so maybe retry or abort, depending on how you set it up and what NSO should do in that case. Preferably, you of course want to avoid conflicts, and we'll get to that too. Here now, then we are in the critical section where we're updating the database, we're updating CDB, we are doing preparations of the NEDs, we preparing the commit queues if you're using the commit queues for this transaction, and committing to CDB. So we don't want several transactions committing to CDB, of course, at the same time. That will produce bad results for a database. So therefore you have this lock, and when CDB updates are done and perhaps we push something into the commit queue, then the lock is released. So so this is then the critical section. The other transaction will either, depending how you set it up, most of the default setting is that the other transaction will wait here for the transaction before it to complete if you had concurrent transactions in this case right here. An alternative to using commit queues is of course using network-wide transactions, which means that in this critical section the device will be updated as well. So if you have a slow device, that will definitely extend this critical section, which is where the lock is taken for quite some time, depending of course on the device or devices. It might be updating several at the same time here. Yes. So an important part is to measure. You can do something stupid, something silly. It's not stupid, it's actually smart. You can do something simple. If you want to measure things, you can use, of course, the observability exporter, progress trace logs, and so forth. But really, if you're looking for performance of transactions, you want to know, okay, well, how much wall clock time does actually my transactions or transaction take to go through all these steps? And you just measure that. Maybe you want to also check, okay, how much memory does this consume? And you just check the RSS, the resident set size, and the high watermark in Linux that's available there. And just use some simple Python scripts for monitoring performance. Sure, I mean, this is helpful if you have like small tests that you want to run and so forth. A powerful thing is the progress trace, and especially when you visualize it and you can see exactly what's going on inside of the transaction, which is then the purpose of this progress trace. Here you can, this is a small Python script which comes with example set. You can use a much more elaborate variant of this with the observability exporter, get the live view and all these sorts of things. Let's see if I can get it up here. Here we go. And we have to make things bigger, I think. Anyway, there is in the example set under the development guide, there's these concurrency model examples, which is what this presentation of the lab later is kind of based on, or is based on. And then under the common folder here, you have the little script that actually does the very simple way of visualizing this progress trace. It's just a few lines of Python, basically using the rich plugin, so you need to install that, or package, as I should say. Let's go back. All right, so here you can see the transaction. you have rest_conf edit. There's a span. This is the duration of the rest_conf edit, 5 seconds. You have the transaction hook, the part which then goes into the service create, and these things are called here. So here you can see that the service create take about 2 seconds here in this progress trace right here, and there's a validation phase which also takes a couple of seconds, and then the updated device or devices in this case, there's the one device actually in this case, it's just one. So it's holding the transaction lock, pushing the configuration up. And that's okay, so there's 2 of them, so that means there's 2 devices in this log right here. And you can see how that's done then in parallel in this case right here. All right, so what do you want to focus on when thinking about transactions here, and if you want to minimize the span of a transaction time-wise? Well, if you want to have any concurrency, you need several transactions going on to update the database, to update CDB, and you want to run them then concurrently, because this will enable you to utilize multiple CPU cores, given that you've done some things that I'll show you later here. You want to minimize the time, of course, spent validating or doing the service create update. If you have a service that updates the devices, you want to minimize the time you spend there, so you want to be as efficient as possible. And there's a few ways of doing that that you may or may not have thought of. Then, if you're interested in doing things concurrently, you want to enable commit queues, because the commit queues will make it so that you actually commit to the commit queue, then release the lock so the next transaction can get into the critical section, and the devices can be updated in parallel while the next transaction is actually preparing for updating the next batch of devices, or actually doing it at the same time. So if you look at this, this is like a summary of the transaction with the same colors and so forth. You have the service in blue right here, and you have the green part, which is then the validation part, and the critical section in orange. This represents one transaction using one CPU core. So you may, for example, have 3 devices, and you might update them in the same transaction, which will then lead to that, okay, I will only use one CPU core. That's what I will do. I will do the service create in a sequential order. I will do the validation in sequential order. And then I will, in parallel, instead, actually send the configuration out to the devices. But the critical section will be, will of course be longer, because I'm updating all 3 at the same time. Compared to then, if you divide this up into 3 transactions, 1 per device, which is a good design pattern. Having a service, for example, you might have a service instance that maps to 1 single device, which is a good design pattern then to achieve this. So here, now you see that, okay, the service work is done in parallel on each on its separate core. The same thing with the validation part. The only thing that's not done here in parallel is like updating CDB and updating commit queues, which is done then inside of the critical section. Right. So this is what the result you have. 1 transaction to all devices means that you're using 1 CPU core. 1 transaction per device. You might have 100 devices, then you can run them on 100 cores, basically. In theory, at least. Okay, so this is what then 1 transaction per device for 2 devices would look like in the progress trace. Here you can see the different colors. That's different trace IDs or different transactions. Is what it actually also is in this picture here. So here you can verify it. Okay, if it looks like this, then okay, I achieved what I wanted to do. The service create is done in concurrently, the validation phase done concurrently, and then here I'm hitting the transaction lock. This is not done concurrently. One of the transactions has to wait for the other to pass through this critical section, right? So that's what you see here, being sequential then for updating device or for updating CDB and updating commit queues. If you compare this to NSO 5, this is the way it was done then in NSO 5. I mean, even if you had done all this work and you divide it up into different transactions, one per service instance, for example, the transaction lock was taken right after the read-write phase, right after the minimum diff calculation. So all through the create phase and the validation phase, the lock was taken. So then the transactions, even though they are running each on, this could run basically on the same CPU core. It probably would in that case, because transaction 2 has to wait for transaction 1, and then it's transaction 3's turn. So there will be no concurrency. Also, what improved with NSO 6 compared to 5 was the dry run and service check sync, for example. That can be done in concurrent or parallel calls. Right, if you want the same behavior as with NSO 5 with NSO 6, all you have to do really is to use this NCS conflicts with where you define your service, and you're back to NSO 5 basically. So then you have a conflicts with the service write lock, then serves the purpose of having each transaction wait for each other after the read-write phase, just as with NSO 5. So you can use this conflicts with itself. For example, if you then start one transaction per service instance, you will have that behavior that the lock is taken, and the create phase and validation phase won't run in parallel or concurrently then. You can also use this conflicts with extension to say, okay, this service conflicts with this other service, so you can multiple conflicts with statements here also to make sure that, well, this service should not run when this service is running or something like that. And this third service may not run if this is running either or something. Okay, so let's look at what we can do to minimize the time in the create and the validation phase. So, like I said, here's a visualization of the design pattern I was suggesting that these examples are based on. That's okay. I'm not with my service. I'm not my service instance. I'm not updating several devices at the same time. Instead, I want to limit that to update one device per service instance. And if I do want to update several devices with one service call to make it easier for someone who's using this northbound API or something to update, I can place a customer-facing or a CFS on top of this service. So you can have a stacked service for that. You will still achieve this performance here if you manage to then separate the CFS so that it creates several transactions at the same time. And there's a trick to do that. You use nano services, and I'll get to that. All right. So another thing that you can do to speed up, which I saw one user do already with the Java API, you can do it with the Python API as well, is to not use MAPI shared create set element or the magic create and then set the leaves one by one. That will mean API calls and things being done for, you might have in this case, the user had several rules for an ACL list and also routes want to be updated. If you update those from the service, and there's a huge number of those, let's say 3,000, 10,000, in this case it was 12,000, right? Something like that. Then using shared create and set element is quite inferior to using just shared set values, which would then do a bulk update of all the list entries at same in one call basically, and that would save a bunch of time. So in this case, there was this picture here. You see the create phase then went down for 3,000, I think, rules in this case from 3 seconds to 7 seconds. So quite an improvement in that case, just by using something that updates list entries in a bulk, or several things. It doesn't have to be list entries only. It can be all sorts of things that you put into one call with set values. And there's a way of using, with the Java API, you can do that with XML. You can look at the example if you want to do it right now with Python. We are looking at updating the Python API, so it also can take XML. Otherwise, it takes right now it takes the internal kind of format of the tag value format that CDB uses, which is a bit tricky. You have to traverse the schema and so forth. But look at the example that I will point you to in the example set for concurrency model, and you will get an example on how to do that, even if you have XML. Okay, so then using commit queues. Why do we want to do that? Well, if we use network-wide transactions, if we use several transactions. Okay, if we just have one transaction, and that goes to several devices, NSO will update the devices in parallel or concurrently when it's time to do so. If you updated 3 devices and you are not using commit queues, but you're using just one transaction. The difference is if you have several transactions going on concurrently. As you can see here, then you have the critical section will contain the update of the device too if you're not using commit queues, which means that the next transaction will need to wait until that critical section is over, like you see up top here. Yeah, I need to remember to turn this on sometimes. Then with commit queues, of course, then the critical section will be just, okay, updating CDB, updating the commit queues, and then I'm done. And I don't have to wait for the commit queue to finish pushing the configuration down to the device. So of course you save a bunch of time by just doing that as well, if you have transactions going in parallel, to be able to utilize all these nice CPU cores that you have at your disposal nowadays. Right, here's the progress trace then of when we actually use commit queues. Here you see that if you remember the previous picture, this was not done in parallel, and here it is now, done at the same time. 2 transactions, and they go through the create concurrently, they go through the validation phase concurrently. That takes some time because there's some work done here in this example, and then the updating of the devices is done also in parallel. So everything is nice and parallelized. We're using the CPU cores that we have. We just need 2 CPU cores for 2 transactions in this case. And we're maximizing the utilization of the concurrency here in NSO with minimizing these create and validation phases, making sure that they can run in parallel by having several transactions going at the same time with NSO 6, and then pushing the config to the devices using commit queues. So why would you want to turn off the commit queues? Well, and why do you want to use it? And why do you have to make that choice? Well, if you look at the CAP theorem, which is a popular theory to look at, like if you're looking for concurrency parallelism, there you can have consistency and availability, but then you basically don't can have multiple cores running at the same time if you want both consistency and availability. Or you can have multiple devices, I would say just one device in this case that you're updating one transaction if you want full consistency, full availability. If you want availability and multiple devices, multiple things being done concurrently, with commit queues, you will have to sacrifice some consistency. And this is of course that, okay, CDB is updated, the commit queues are populated, now you let the next transaction in. So what happens if something fails? Well, you can use, you probably have turned on the commit queue rollback on error, which will happen, but for a split second there, you will have something that is not verified on all devices to be correct. Some of the devices might have been updated, and now the inverse of that configuration needs to be sent to those devices who were updated because one of the devices that you wanted to succeed didn't succeed. So you have a window of eventual consistency instead of full consistency like you have with network-wide transactions. And basically this thing in the middle here is pretty hard to achieve. You want to, of course, get as close as possible to having all of these nice things, doing multiple things in parallel and still having the best availability and concurrency possible. And that's what we try to do with NSO here. Okay, I mentioned nano services and CFS things. What can you do with those? So a nano service can be used to not speed things up necessarily, but simplify. So you may not want to have several RESTConf transactions or several CLI sessions doing commit at the same time to achieve this concurrency here to deploy to multiple devices. What you can do then is you can actually use a nano service that will help you divide this one transaction into multiple components, one component per transaction, for example, like in this example here, which then updates one device, the design pattern we talked about. That is because nano services can be set up to do things it does things in multiple processes, and it can be set up to do them in concurrently for us and do that work so that we don't have to send in 10 RESTConf transactions if we want to update 10 devices. We can just update one thing, and then that will take care of splitting things up into different transactions. And then multiple processes, one per transaction, using multiple cores. So we can just create a very simple nano service. We just have to add the init mandatory and ready state. That's mandatory in our plan for the nano service. And now this will, instead of sending in 3 transactions, we have just one that spawns then 3 different transactions. That is just the critical section is the only part which is not running concurrently or parallel. We can add some things like this example does, an example set. We added the validate state. This is not something you need to do, but you can. Like a validate state and a configured state where you have the create callback going out. You could have the create callback here in the init state, for example, if you wanted to do that. Yes. So if you've done the work here and you went through all of this process here, you were doing a good job. You have multiple transactions now. You're using all the CPU cores on the device, and you maximizing the capabilities you have of the hardware. You minimize the create phase, validation phase, and so forth. You're using commit queues. Really made sure that you've done what you could. Then you can actually use a nano service and then together with a CFS to actually scale up to put in one more multi-core processor, for example, to have another 100 cores or another 10 cores, depending on how many you have on your CPU. So the first step to do that would be to simplify. Like you can do that without scaling up into several devices. You have a CFS, a customer-facing service, that may simplify the Yang model that goes down here, because this one is the nano-service Yang model, and you want to expose something else perhaps. So you could have a CFS there. So what you would do then is to have this CFS. This is a very short little transaction that then spawns these larger transactions, for example. That's something you could use. The benefit of having a CFS is now your service is modular. which means that now you can scale up to have several multi-core processors. Let's say we have a single core processor, just because I don't fit so much on one screen. So let's pretend that we have a processor with one CPU core here, processor with one CPU core here, but we have two transactions. How do you do that? Well, then we would place our CFS then on another processor somewhere, or the same as this one or whatever. And then we would use that CFS to do transactions through LSA, an LSA setup, to these nano-services that then would spawn multiple transactions. It would be just one device if we had a single core processor, but say we have a multi-core processor, then this could be 100 devices, 100 cores for this device right here, and this multi-core processor could update the 100 devices, and then we could just add, and we can update 10,000 devices using our 100-core processors, like 10,000 divided by 100. That's how many processors we would use, multi-core processor we would have to use for doing that. So this is quite powerful to scale, and if you're not interested in running things concurrently and you have conflicts, then don't do this setup, basically. Right. So now we have three transactions here. One CFS transaction, and then we have one transaction per device. In this case, we have 6 devices. One multi-core processor is running 3 transactions. The next one, because there were only 3 cores perhaps on this picture, it's kind of incomprehensible to put up 100 here, so we stick with 3 here. We have a very small multi-core processor. But then the next multi-core processor would run another set of 3, and like I said, you could just increase this as much as you want. This transaction here will grow just a tiny bit, but that time here spent on this transaction would hopefully then be insignificant for you, the CFS. That's how you want to design it. So you want to have insignificant work being done for this transaction, but then all the work is done on the RFS nodes in the LSA setup. Yeah, and that was my last slide. So in 30 minutes, we'll go through the examples for this and also the lab for how to achieve this. And you can check this out in the example set under the concurrency model. That's where you have the examples that we'll go through in the lab. You can take a look at the lab. You also have a playground for running NSO if you don't have NSO installed. But if you're using this playground, you have basically a two-core multiprocessor. So you're quite limited. But anyway, 2 cores is enough to play with this. The development guide chapter, scaling performance optimization, recommend that. Concurrency model, very good at explaining conflicts and so forth, that chapter. And then you have the user guide for commit queues, and for LSA, it has its own guide. Thank you.
Thank you, Conny. We have maybe a couple of minutes for questions, if there are.
Hello. Looking at the time spent for the transactions, even in the most concurrency model, the best one, you have to wait for the critical section of multiple transactions in parallel to be complete and cannot be parallelized.
Right.
And later on, the configuration is delivered to the devices. And it's usually the part that takes too long. And not all the devices answer at the same time. So maybe in parallel transactions, there are devices that finish the configuration before than others. Is there a possibility to move that part of the updates CDB, the critical part, to the end, to avoid also in case of failure of the transactions into the devices, not to delete that part from the CDB, because if you right now you are updating the CDB, and if something happens bad in the transaction to the device, you need to remove that from the CDB, and you also fall in the critical section. But if you put this part at the end, maybe you avoid updating if something goes wrong with the device, and you just update when the device answer and can improve a little bit more.
Let's see if I understood this correctly. So without commit queues, you would just have a network-wide transaction. If anything goes wrong, devices are rolled back. If they're netconf devices and they had a candidate data store or something like that, then nothing would be updated on devices. On devices with CLI, they would still be updated, and then NSO would have to send some undo information to that device, even if it's network-wide transactions, and no commit queues. Then NSO would go and roll back CDB in NSO as well after that is done, or when that's done. You would still have the critical section, so no other transaction would enter when that's done. With commit queues, you have this, which you typically have turned on, like the rollback on error. So that will take care of basically rolling back the device that had an error, or actually the whole transaction that was done there. So if you updated several devices with one transaction, it will roll back all of them. So if you have one transaction per device, yes, if one fails, the others would be updated, and you would have to roll back them yourself, yes, using CLI. So extending then the transaction lock to cover then the commit queue is your question, if that's possible.
It's one slide more. Later, when you have all the transactions in parallel, the order to execute right now is that the critical section is before sending the commands to the device. I say, if you put that critical section at the end, after sending the commands to the device, could you think?
No, NSO works in that way. If any of my colleagues have a better answer, we want to update CDB first. And then we want to send the configuration to the devices, and this is.
I know that. That's my question.
Yes.
In a failover situation and all sorts of other things, it will break.
Yeah, we'll get into trouble if we do that.
If you have a failover in the middle of that, you have to continue doing that from the other host layer, right? Or if you need to roll back, so all this data needs to be in the database first. There's no way around that if you want to do anything that's reliable.
Okay, thank you.
Yeah, we want to keep things safe still, yes. I fully agree with Jan said, yes.
Okay, thank you. I think we are out of time. So, you have a short question, maybe?
Yeah, I hope so.
Well, it's just coffee.
Whoever
after
wants
this.
to go for the.
I hope it will be yes or no. So, continuing the previous question, when we use nano services to parallelize execution, and one of transaction fails due to device cannot execute it, will the rest of sub-transactions roll back, and the parent transaction roll back automatically, or not?
Yes, as I understand, yes, they will be rolled back, because there's one transaction basically that kicks off the nano service that then makes multiple processes out of this and does the work. So if you have one transaction that commits several nano service components, which is then in this case representing a transaction each, all of that will be rolled back if something fails.
Okay, great, thank you.
Thank you. Any more questions? Quick ones?
Yeah, see you at the lab after coffee then.
Thanks, Conny.